station. The sun may rise in the east, at least it's settled in a final location. It's understood that Hollywood sells Californication. Pay your surgeon very well to break the spell of aging. Celebrity skin, is this your gender? Is that war you're waging? Firstborn unicorn, hardcore softcore. Dream of Californication. Dream of Californication.
Okay, can you hear me? Can you hear me okay in the back? Can you hear me at the back? All right. Welcome, EECS16A. Woo! Okay. So unfortunately, Anna's still not that great. So. Pretty bad cold. So she apologizes and says hi and stay healthy, everybody. Again, I'd like to thank everybody's here. Thanks so much for coming to lecture. Such a nicer experience for me as well as hopefully for you. And we definitely think that this is the best way to keep track with class. So midterm is coming up, midterm 1, which will cover basically everything in lecture till today, including, but also will cover Monday's discussion. Okay, and this is tomorrow is going to be the last homework before the midterm. Exciting, first midterm, right? For some of you. Who had already a midterm this year, this semester? Okay. I've been asked to put this announcement. If you have any DSP accommodation, send the letters to us tonight. If you want us to do anything about it. I don't know. If you have a DSP letter accommodation, just send us by tonight, okay? I mean, I know that left-handed desks are really important. Left-handed desks are really important. I know. I've lived through that. Okay, last time we talked about computing the determinant. That was fun. Remember? Right-hand side, plus, multiply. Positive sign. Multiply, negative sign. Add together and then you get a 2x2 matrix determinant. We also talked about eigenvalues and eigenvectors of matrices, and we kind of gave example of PageRank, where there we had the steady state kind of vector, and we showed that, oh wow, that thing happens when you have effectively looks like a kind of an eigenvalue 1. Eigenvectors with eigenvalue 1, and we extended it to general eigenvalues which are not 1. And I showed you how to compute eigenvalues. And so today we're going to continue talking about eigenvectors and eigenvalues and eigenspaces and all that good stuff. Why is the screen kind of going on? Causing jerkiness to it. So that's what we're going to do today. You know, eigenvalues and eigenvectors is one of those things that that a lot of people learn in college, you know, in linear algebra classes, and they just can't figure out what it's used for. And so we're going to try to teach you kind of what, you know, this is actually one of the most important concepts when analyzing a system. It's eigenmodes, it's eigenvectors, you know, what actually happens to the system, how does the system behave to predict how a system behaves. Remember, systems can often be described by matrices, and if we know the eigenvalues and vectors of that system, or can design them, we can control that system property very easily and understand what that system does. And so it's a hugely important topic, okay? Especially, if you think about PageRank, right? That's a $1 trillion industry, or whatever, search kind of industry, right? That's really big. So it's really important concepts. We're going to deal mostly with 2x2, 3x3 matrices, but it doesn't have to be. It could be, we think of it of a million by million matrices, right? Like when you have very complex systems, when you have spacecrafts, going to, and when you have, or some other control mechanism, or even biological systems. Sometimes if you can describe them using linear systems, that went away. You want to describe them by a linear, by that. Okay, let me see what's kind of going on here. Okay, no lecture today. Doesn't look like it's stable. So I have a very good colleague. Let me tell you a story while I'll try to figure that out. I have a great colleague, Anita Flynn, and she has she always says that it's always a connector problem. Like anything can be reduced to a connector problem, and she's always right. Because that's actually the mode of failures. I think it's the HDMI cable. But let's try to see if that works. I'll try not to move. Okay. All right. Let's try to recall what we've done so far. Okay? Let's just think about that, right? Because it's always good to stop for a second and kind of reflect, right? Reflect of what we've done, what we're going to do. Okay? So what we've done so far? Well, we talked about linear set of equations, right? We took some problem and just tried to describe it, linear set of equation. We saw that, important problems can be described that way. We talked about matrix and vector multiplication that can also describe a linear set of equations, right? In a very interesting way, and like how to multiply, we did like this, like that, and all that kind of good stuff. Once we describe these linear equation in that form as matrix vector multiplication, we showed how to solve it using Gaussian elimination. Not the game, but the algorithms, right? We are able to solve then very efficiently the system of linear equations. Then once we have those, we want to say, well, what can we actually reach, and what is possible and what's not, and when do we have a solution, and when we don't have a solution, where the solution is unique, right? So we talked about span, we talked about linear independence, and all that good stuff. Then we looked at matrices transformations, right? We take some vectors in, and then vector comes out, and something happens to those vectors. They are rotated. They are they translated? That would not be linear. That would be affine, right? So translating a vector, that's not linear. But they are rotated, they're reflected, they're scaled, right? All this things that matrices can do. And then we say, well, what about the situation we want to undo what we just did? Or maybe something did something, and we want to get back what that something was done to it, right? Like we want to invert the system. And so we talked about matrix inversion, how to compute it, when it can be computed, what are the conditions that it can be computed, right? And then we talked about column spaces and null spaces. And null spaces is an important concept where this is the space where vectors are invisible to a matrix. A matrix, a null space of a matrix, any vector that comes from the null space will be mapped to zero, to the zero vector immediately after that. So it doesn't matter what comes in, the matrix kind of like, just not, it's blind to it, right? It will just, black, go to zero. So this is also very interesting. It means that there can be a lot of solutions, or maybe no solutions to a linear set of equations when that happens. When we talked about null space, that led actually to an interesting point, because we talked about the steady state situation where we have a steady state vector with a transition matrix. So a vector comes in, matrix is applied to it, transition matrix, and then you get the same thing. And we said, oh, wow, that's interesting. That's a steady state vector. But then if we kind of massage it, we can make it into a null space problem of this matrix Q minus I, and show that, oh, wait, that steady state vector is a null space vector in this Q minus I. Okay, so, and then that led us to discussion of eigenvalues and eigenspaces to really understand and interpret what a matrix transformation is doing. Okay, so, okay. So here's an equation that absolutely worth tattooing on your arm or something, actually somewhere visible. Okay, so beautiful, beautiful. Just stare at this. Wow, I gotta get some perspective over here. Wow, take a look at that. You know this. You think of it as simple, right? Like you just, oh yeah, it's eigenvalue, eigenvector. No. But just think about it. Normally, you take a matrix and you have a vector, and I tell you, oh, multiply them, right? Okay, we'll multiply them like this, like that, like this, like that, like this, like that, like this, like that. There's actually quite a bit of computation that's required in order to do that, right? You have an n-length vector, and you have an n by n matrix. That's n square amount of calculation in terms of its complexity. Okay? All right. Well, if we have this very special vector, which is the eigenvector, that matrix multiplied by a vector, well, the same vector comes out, only just scaled. That's just n calculations, right? It's not n square calculations in order to figure that out. It's just n. So it's kind of linear with a dimension. It's like very fast to compute something like this. It's also very simple. The same, one thing comes in, and it just scaled. It's not rotated, rotated, reflected. It's just scaled, keeps the direction. Wow. That is extremely useful. If we have these kind of vectors, right, that these are very special ones, that the matrix really, it's like, oh, wow, you're going the right way. We're not going to change your direction. We're going to slow you down, shrink you, or we're going to like speed you up, expand it, but like we're not going to really change your direction. Okay? Now, if you look at this, there's a few things also that you need to know. A has to be square. Otherwise, no, A has to be square. Why? If it's non-square, it just doesn't compute. You do like, you type it, and it just like, it does like syntax error. Because how can you take A times V equals lambda V if it's non-square? The result is going to be the same, different size if it's non-square. Or you won't be able to multiply by V. It just doesn't compute. It has to be square. Okay? Does that go back? That harp thing? Okay. What about lambda? That eigenvalue. What could it be? Anything but 0. Really? Why should it be 0? It could be anything. It could absolutely be 0. In fact, matrices that have linearly dependent columns or have the null space, they'll have eigenvalue 0 because that's the direction, those vectors that are going to be crushed, right, to 0. That's going to end up, right? That's really also another interpretation of that. If you have an eigenvalue 0 and you have an eigenvector associated with that eigenvalue, that V is going to come into the matrix, and that eigenvalue 0 is going to crush that vector to 0, and the output is going to be 0. Do you see that? Okay, so absolutely could be 0. It could be actually any number. You know what? It could also be complex valued, but that's 16b. It's not 16a. Okay, so any number for eigenvalues. What about eigenvectors? Okay. What about eigenvectors? Can they be anything? Any non-zero vectors, because if it's zero vector, it doesn't make any difference. I mean, like there's nothing informative there, right? If it's zero vector, yeah, sure, or whatever, you know. Something times 0 is 0. We know that. Okay, so we're not looking for the trivial cases. We're looking for the non-trivial cases. So yeah, so anything but 0. Okay, so I said actually what is lambda 0 means, and lambda 0 means that there is really a null space. That's really what it means. There are some directions that a vector will come in, it will be crushed to 0. That's what it means. Okay, vector comes in, it's scaled. It's scaled to what? Dead. And when his parents dead, when his family dead. You seen that movie? No. It's too old. Reference movies. That's when you know that you've been teaching too long. Is when students go like, oh, you don't remember that reference from like 1974? Oh yeah, that's right. Untouchables. Untouchables. That's a good movie. Okay. So eigenvalues and eigenvectors. Let me just go back for you and refresh the definition. The definition is the following. Let A is a matrix square, and then lambda in the reals, and again, in general, lambda is in the complex realm, but 16A, we're dealing with reals. So we're saying if there exists a vector v that's non-zero vector, such that A times v equal lambda v, then lambda, that lambda is an eigenvalue of A, and v is an eigenvector associated with that eigenvalue. And then the null space of A minus lambda I is the eigenspace of, it's the eigenspace. Okay? So that's the definition. And there was a disciplined approach of how to go about in calculating them. Right? We said, oh, you have A times V equals lambda V. That also means that A minus lambda I times V equals 0. That also means that. Can you see that? I'll let you digest this for a second. Some of you at least. Digest. Right? AV equals lambda V. You take the lambda V to the other side. You take the common multiplier. So it's A minus lambda I times V equals 0. That means that V is in the null space of A minus lambda I. And now we need to find both the lambda and the V that is associated with it. Now, what does it mean to find the lambda? Well, this means that V is a null space vector, like vector that spans the null space of A minus lambda I. That means that A minus lambda I has a null space. So we need to find first a lambda that satisfies the condition that A minus lambda I has in fact a null space. Because it may not have a null space, right, for all possible lambdas. And so what we're going to do is first, we're going to form this matrix B lambda, which is A minus lambda I. Okay, that's the first thing we're going to do, is just form this matrix. That matrix, we're going to look for its null space. Okay, then we're going to find all the lambdas that would give us a non-trivial null space. Okay? Not all of them, not all lambdas are possible. It turns out if it's a 2 by 2 matrix, there's only 2 of them. Okay? So we were going to find all the lambdas resulting in a non-trivial null space for B sub lambda. How do we do that? We learned last time that when you have a null space, what entity or what operation that we compute on a matrix would result in some, like how do we guarantee that we have a null space? Maybe in the back. Think about that. What did we do to find lambdas? Determinant. If the determinant is 0, then we have a null space. So let's compute. Now we have a parameter lambda. So let's compute the determinant with that parameter lambda and find those lambdas that would give us the determinant being 0. So we're going to solve the determinant of b sub lambda equals 0. When you do the determinant with that, you'd actually get an nth order polynomial. If b is size n by n, then you get an nth order, and we call it a characteristic polynomial. A characteristic polynomial. Okay, we have a specific name for this, so important. What's the polynomial name? Characteristics, that's right. Or characteristic, if you want to speak in proper whatever. Okay. A polynomial, and that turns up to be an nth order polynomial. Okay? An nth order polynomial has n solutions. And so there's going to be n of them. Now, a polynomial of degree 1, that's easy, right? That's very simple. How many solutions have a polynomial of degree 2? It's a quadratic equation, right? Quadratic equation, how many solutions? You were saying something? No, you. 2. That's right. And what about? Is there an equation for that? Can you find it explicitly? Degree 2? Yeah, for sure. There is an equation, quadratic equation. I always forget it. What is it? What? Negative b plus minus square root of 4, b squared minus 4ac divided by 2a. There you go. I actually remember it. What about a 3 by 3 matrix? Do we have an explicit solution? Is there an equation for a 3 by 3? So a third order polynomial. Is there? There is a really complicated one. That's right. What about 4? There's a super complicated one. What about 5? 5 there isn't. You can actually prove that there is no equation. People have proved that. You cannot solve it, with symbols and stuff like that. It's not possible. You have to solve it numerically. Okay, so above 5, everything is then solved numerically beyond that. Okay? Each solution of this polynomial is an eigenvalue. And once we found these eigenvalues, for each one of those eigenvalues, we're going to find the vector space, basically the null space of b sub lambda. Okay? For each one, we're going to go, lambda 1, we're going to find the null space of b sub lambda. Lambda 2, we're going to find the null space of b sub lambda. Those would be spanned by the eigenvectors. Okay? All right. So here are solutions for the characteristic polynomial. Okay? We have a matrix ABCD or ACBD, depending on how you read it. And what we're going to do now is going to compute the determinant of A minus lambda I. Okay? A minus lambda I is the determinant of A minus lambda, C, B, D minus lambda. What do you do? Okay? Multiply diagonals, subtract these diagonals, and you get A minus lambda, D minus lambda, minus BC. And that is a polynomial of degree 2, right? It's a polynomial of degree 2 because you can write it as lambda squared minus A plus D lambda plus AD minus BC equals 0. Okay? And it has, in this particular case, 2 solutions. And those 2 solutions will have kind of sometimes it's 2 solutions, sometimes not. So what situations we have here? There's a few, 3 cases kind of that we can talk about. That's can you agree with me this is a parabola? Right? Okay. So something like that. You'll have roots. And here in this case, when it's equal to 0, we would have 2 distinct real values. Case 1. Is that a parabola? What is that where that parabola hits 0? One spot. So now we can have 2 same roots, right? Still 2 solutions, but same root. Okay, same value. Oh. I'm going to move it. I'm going to flip it like that. Magic. When does this equal 0? It does equal to 0. But you have to have it complex. Like it's just this parabola doesn't hit. I mean, it's like the solution has to be complex valued. Otherwise, it doesn't work. This is the case when you've got 2 complex eigenvalues. Okay, when you have that kind of a polynomial, the solution's like that. So 2 distinct, single repeated eigenvalue, or 2 complex valued eigenvalues, which we're not going to talk about. We're not going to talk about now. We're going to talk about that in 16B. Take that class. Theorem. Here's the theorem. I'm not going to prove it. I'm just going to show you kind of like I'm just going to tell you how you would generally prove it. But it is an important theorem. The theorem says, if you have a matrix that's n by n, and it has m distinct eigenvalues, m distinct eigenvalues. It could have repeated eigenvalues, but at least m of them is distinct, are distinct. Okay? M of them are distinct. And it has corresponding eigenvectors, so all those VI's from 1 all the way to m, so distinct eigenvalues with eigenvectors associated with them. It is the case that all VI's, all those that are associated with distinct eigenvalues, are linearly independent. If the eigenvalues are different, their eigenvectors associated with them are a set that is linearly independent. Wow, that's pretty cool. What if I have a 3 by 3 matrix and I have 3 distinct eigenvalues? What does that mean about the eigenvectors? They span what? They span R3. 3 distinct eigenvalues, eigenvectors linearly independent, 3 of them, 3 vectors that are linearly independent will span R3. That's useful. That is very useful. Okay. If a matrix, a 2 by 2 has 2 distinct eigenvalues, then V1 and V2 are linearly dependent, and therefore the span of V1 and V2 will be R2, and those vectors, beyond just being linearly independent, they'll form a basis. Okay? They'll also form a basis for a subspace. Does that make sense? Because they'll be the minimum. They're linearly independent, so they're the minimum number of vectors that require to span that space. Okay? Well, you can look at the notes. There's a proof, 9.6.1, and the concept is by contradiction. You assume that they're linearly dependent, and what you'll have is the result that you have either lambda 1 equal lambda 2, or one of the eigenvectors will be 0. And that violates the assumptions, hence they have to be linearly independent. Okay, so you can go through this and practice it, because this is a really nice proof. So either check it out or try it yourself. Okay, by contradiction. So just remember, distinct eigenvalues lead to linearly independent eigenvectors. Fun. Let's try to visualize eigenvalues and vectors. So we talked about matrix transformations. And then I have this AV equal lambda V, and first of all, I'm looking at this. You know, what does this matrix do? What does this matrix do or does? I don't know what you say. What does this matrix do? What does this matrix do? Okay?
So you said that for a 2x2 matrix, that if it had two unique eigenvalues, we form a basis for R squared. Does that generalize to, like, if you had a 3x3 matrix and we have three distinct eigenvalues with span of 2?
Yep.
And any n?
Yeah, so any n, an n dimension, okay, even if you have an n by n matrix, an m, which is less than n, of the eigenvalues are distinct, then the eigenvectors associated, all those m, will be linearly independent. They may not span our n, but they'll span a subspace of size m. Okay? Does that clears a little bit? Okay. So what does this matrix do? It scales what? Scales the y-axis. And what about the x-axis? Nothing, right? So this matrix is a stretching matrix. This is a gray matrix. Like let's say Anna was here and I would apply to her, she'd just become taller. Right? You know, this is the tallifying matrix. Okay? So the matrix, if I want to write it, it keeps the x-axis the same, like this, like that. So it will be 1 and 0. Keeps the same axis the same. And then the y-axis, like this, like that, it multiplies by 2. So can I? Is that a right matrix? That's what this matrix really does. It scales. It doesn't scale the x-axis, because if I put a vector here, and then this is the x and this is the y, right? X stays the same, y is twice the size. Okay? All right. And now I want to compute the eigenvalues of that matrix. Now, it's a little bit stupid because it's a diagonal matrix, but I'm still going to go through that process. So the first thing that we're going to do is we're going to compute b sub lambda, which is a minus lambda I, and compute the determinant to evaluate the Church-Ritchie polynomial. Okay? So this is the determinant a minus lambda I, and it's 1 minus lambda, 0, 0, 2 minus lambda. Compute the determinant. I get 1 minus lambda times 2 minus lambda minus 0 equals 0. Can you see the roots? Can you see the roots? Let me actually just give you a hint. When you see a diagonal matrix, its diagonal values are the eigenvalues. Okay? If you see an upper triangular or a lower triangular matrix, also the diagonals end up being the eigenvalues. Remember that. That's a good tip. It just comes down from the way you calculate the determinant. Okay. All right. So we have two values, lambda 1, lambda 2. Lambda 1 equals 1, lambda 2 equals 2. That means, what does it mean? That in the direction of eigenvalue, the eigenvector associated with lambda 1, things will stay the same. In the direction of eigenvectors associated with lambda 2, things will be scaled by 2. That's what it means. But now we need to find those directions. How do we find those directions? We look at the null space of a minus lambda I for each lambda separately. So we do that for lambda 1. Lambda 1 is equal 1. So you put 1 instead of this lambda, and you get 0, 0, 0, and then 2 minus lambda gives you 1. That times v should be equal 0. And you ask yourself, okay, what does this vector, what is the span, basically what is this, what is the null space of this matrix, basically? That's what we were trying to look for. Okay, how do we do that? Gaussian elimination, right? This is a linear system of equation. We want to find that, basically, what is the vector v that does that. And so I'm just going to write it, 0, I just flipped the, I changed the row, the order. And so it's 0, 1, 0, 0, 0, 0. Oh, that's pretty easy. basically this vector, x, like this value x2 should equal to 0, and then x1 should be arbitrary, right? x1 could be arbitrary. That's basically the solution. So the second element is 0, and then the first element is a free variable. And that means that my vector v1 associated with lambda 1 is the span of 1, 0. Okay? Let's see. I'll take this matrix, multiply by 1, 0 is 0. Yeah? This matrix, I'll get times that, I get a 0. Okay? It is within the null space. All right, so now I found the span of 1, 0 is the eigenspace associated with lambda 1. I'm going to do the same now for lambda 2. Okay, so 1 minus 2 is minus 1. 0, 0, 2 minus 2 is 0. And now I need to solve that. Okay, how do I solve that? Gaussian elimination. I flip the sign on this one. I get 1, 0, 0, 0, 0, 0 here. And what does this really tell me? It tells me that x1 equals 0 and x2, or sorry, the second variable is the free variable, and the first one is 0. That means that v2 is in the span of 0, 1. Okay? Any questions? Simple. Because it's a diagonal. Yeah.
What's the eigenspace?
The eigenspace associated with lambda 2 is the span of 0, 1. Okay? Anything along the y-axis, right, is going to be scaled by 2. Anything along the y-axis is going to be scaled by 2. Anything along the x-axis, which is this vector, that's the span, it's going to stay the same. That's kind of what the matrix did. That's what came out of it, right? So that's what also it says. Okay? So you stare at this long enough and you see, oh yeah, the y-axis, the green arrow, scaled by 2. The red arrow didn't change. Now what about the yellow arrow? Like what about if we take now an arbitrary vector? Now we know if we take vectors in the like in eigenvectors, we know what's going to happen to them. They're either going to scale or stay the same. But what about the yellow one? What's going to happen to the yellow one? Okay, think about it. Everybody's quiet. The yellow one, it started as a 1, 1, actually. So this yellow one, if we actually go back, that yellow one started as the vector 1, 1. And then it ended up being something else, 2, 1, right? 1, 1, 2. And that's what it ended up at. Okay, so it's actually not keeping its direction. Yeah, its x component, it's like x-axis components stay the same, and the y-axis is doubling. That's what we figure it out. But what I want to actually interpret it, I want to interpret it in terms of eigenvectors. Because when I actually stare at this, the vector 1, 1, the vector 1, 1 ended up being 1, 2, right? That's what happened to it. But what is 1, 1? When you say 1, 1, what is it? It's like 1 in the x direction and 1 in the y direction, right? So you can also think about it as a linear combination of vector, right? 1 times the vector in the x-axis and 1 times the vector in the y-axis that you add them together. Let's try to think of this vector as a linear combination of the eigenvectors and see through that how things are changing. Okay? So if, in fact, I have a matrix that this, and it has lambda 1 equal 1, lambda 2 equal 2, okay, this is the eigenvectors. V1 is 1, 0, V2 is 0, 1. I know that AV1 is 1 times V1. I know that AV2 is 2 times V2, right? A V1 equals 1 times V1. Why? Because that's the eigenvalue. The eigenvalue is 1. V2 is the second eigenvalue associated with lambda equal 2. Then AV2 equals twice V2. Now I'm going to bring a vector in a different direction. So what about this one, 1, 1? Okay. I can write V3, that's 1, 1, as 1 times V1 plus 1 times V2. Can I write it that way? It's a linear combination of other two vectors. Those are eigenvectors, though. Now, I'm going to compute A times V3. A times V3, well, hold on. V3 can be expressed as a linear combination of the eigenvectors. So it's really A times 1 times V1 plus 1 times V2. I can open those brackets. What is A times V1? It stays V1, right? A times V1 stays V1. And what about A times V2? 2V2. 2V2. Okay? So A times V1 plus A times V2 equals to V1 plus 2V2. Now, I mean, this was easy, right? This was because it was diagonal. It's like simple. But imagine a 3,000 by 3,000, matrix. When I know the linear combination, like if I have an arbitrary vector and know its linear combination using the eigenvectors, then all I have to do is just scale each one of them separately, and then I can find a solution. We'll do another example. So that equals to 1, 0 plus 2 times 0, 1, which is 1, 2, which we already got. But I want you to think about that in those terms of the eigenvectors. So the fact that I have an arbitrary vector, which is not an eigenvector, it's still a linear combination of eigenvectors. So the matrix multiplied that linear combination is easier to interpret. Yeah. What?
Can you do this with any of the vectors?
Yeah, I can do it with any vectors. Let's do another one. Actually, remember this problem? This one we solved, this matrix, we solved for its eigenvalues and vectors just at the end of last class. That's half, half, 0, and 1. And we said, oh, there's an eigenvalue 1, that's half, associated with eigenvector 1 minus 1. And there's a lambda 2 equal 1 associated with the vectors 0 and 1. Okay, that's what we did last time. So now you know the eigenvalues, and you know the eigenvectors associated with them. Here's, okay. Now these are two distinct. We said by the theorem that V1 and V2 should be linearly independent. We said, right? Are they linearly independent? Is 1 minus 1 and 0, 1 linearly independent? Yeah. Yeah, they are. So they are actually a basis for R2, right? We can use them as a basis for R2. Okay. So now the question is, what is A times V3? Where V3 is the vector 2 and 2. I want to know what's going to happen to that. That's an arbitrary vector, right? It's not in the direction of 1 minus 1, and it's not in the direction of 0, 1. I want to know what's happening to it. Well, V3 lives in R2. V1 and V2 span R2. Can we find a linear combination of V1 and V2 that would give me V3? Yeah. So let's find them. So what I'm actually going to try to find is some alpha and beta such that V3 equals alpha times V1 plus beta V2. Okay? How do I do that? Well, I'm posing as a linear equation. Okay, what is alpha V1 plus beta V2? Right? I know V1, I know V2, I don't know alpha, and I don't know beta. right? But I know V3. Okay? So I can write it as this is V1, this is V2 times alpha beta equals 2, 2. Okay? Now I need to solve for this alpha and beta. How do I solve for it? Gaussian elimination, or compute the inverse of this matrix and multiply by that. There's many solutions. But when I solve it, I do Gaussian elimination, I get 2 and 4. Alpha equals 2, beta equals 4. Okay? Through Gaussian elimination. What does that mean? That V3 equals 2 times V1 plus 4 times V2. Does it make sense? Let's do the calculation. 2 times V1 is 2 and minus 2 plus 0 and 4. 2 minus 2 plus 0 and 4 will give me 2, 2. Okay, so yes, it works. Do you want me to write it down? 2 times 1 minus 1 plus 4 times 0, 1 equals 2, 2, and 2. Okay, all right, so math works. Okay? Okay, well, what's the point? Well, here's the point. The point is that I want to compute A times V3. But I want to think about this multiplication in terms of the eigenvectors and eigenvalues. V3 is an arbitrary vector, but it can be decomposed into 2 times V1 and 4 times V2. Now look how beautiful. I can actually see what's happening. Because the component in the direction of V1, the component of V3 in the direction of V1, right? What's going to happen to it? Well, lambda 1 is half. That's going to be shrinking by half. And what about the component in the direction of V2? Lambda 2 equals 1. Not going to change. So now I can understand what this matrix multiplication does to an arbitrary vector. It looks at it and goes like, oh, you have some component in the direction of V1, let's shrink you. And then the component in the direction of V2, you keep the same. That's what it does. So I can compute it, right? Like it's 2 times AV1 plus 4 times AV2. What is A times V1? A times V1 is 1/2 times V1 because that's an eigenvector. What is A times V2? V2. Okay? So this is 2 times half V1 plus 4 times 1 times V2. Wow, so it's V1 plus 4 V2. V1 times 4 plus 4 V2. Well, now I can explicitly write them. 1 minus 1, 4 times 0, 1. It's 1, 3. That's what's going to happen. I got through, instead of doing this and like that, I got through the solution by looking at what's going to happen in different directions. Now give me another vector, and I was like, oh, wow, I can decompose it into its component in V1 and V2 and understand what's happening to it. What if I don't want to shrink at all? I want to stay the same in terms of height. What do I need to make sure? That I'm always in the direction of V1. Of V2. Otherwise, if I have any component in the direction of V1, it's going to shrink. That's what it means. Okay? Yeah.
So because the eigenvectors are linearly independent by definition, that means that no matter, like, they'll always span R2.
Yeah. They'll.
So
Yeah.
that means no matter what vector you get, so long as it's in that space, you can represent it as a combination.
Yeah. Every vector in that space in R2, I can represent the linear combination of those eigenvectors. Okay? So now I want to make sure, let's say, that my vector length always shrinks by half. What do? I pick the direction in the direction of V1. Okay? All sorts of interesting things that can come up with. I can understand now what's going to happen. Okay? All right. Now I want to talk about a little bit about repeated eigenvalues. I mean, we said, oh, distinct will span R2, right? But okay, what happened when they're repeated? Well, what about this matrix? What's its eigenvalues? I mean, what does this matrix does? What this transformation does, right? It scales, right? It scales both axes by 2. So the matrix is 2 and 2 on the diagonal. Okay? Scales both axes, right? So this is the matrix. And now I want to compute its eigenvalues and eigenvectors. Obviously, because it's diagonal, you know that the eigenvalues are going to be, 2 and 2. But let's just solve it. Determinant of A minus lambda I is 2 minus lambda, 0, 0, 2 minus lambda. That's this. And now I've got basically lambda 1 and lambda 2, both equal to 2. Okay. So now I'm going to substitute 2 for lambda, and I'm going to find the null space of A minus lambda I. Okay. What is the null space of A minus 2I? What happens when you put here 2? It's a 0 matrix. So what's the null space of a 0 matrix? Everything in R2. Okay? The null space of A minus 2I is the null space, right, of basically 0 vector, which is the entire R2. Any vector with R2 that you take a 0 matrix and multiply with will end up at 0. Okay? So now our null space is a 2-dimensional space for eigenvalue 2. So in general, in that case, the eigenspace is 2-dimensional, and in general, multiplicity of eigenvalues will result in a multidimensional eigenspace. Does that make sense? Multidimensional eigenspace associated with eigenvalue 2. Before, when they're distinct, each one of those eigenvalues had a 1-dimensional space. Now, because there's multiplicity of them, they span a multidimensional space. Does it even make sense? Oh, actually, that's mostly true. Because there are situations where the matrix is defective, and that's not true, but that's beyond the class. But in most cases that you will see, that will be true. And so when I look at this transformation, give me an eigenvector. 5, 5. Why 5, 5? Does it keep the direction when I do this transformation? Yeah, it does. What else? Give me another vector. 2, 2. Okay, another one? That doesn't sound like the same number twice? 0, 4. All of them, entire R2 are eigenvectors. Because the null space of A minus lambda I, in that when lambda was 2, was the entire R2. And you can kind of see the direction is, no matter what, all the vectors in R2 keep the same direction. They're just scaled. So if I want to pick a basis, what basis should I pick for this eigenspace? I have a lot of options. I can pick 1, 0, 0, 1. I can pick 1, 0, 0, half. I can pick 1, 1, 1 minus 1. I can pick whatever two vectors that are linearly independent could still be spanning that space. Okay? So when you have a multiplicity, then you have a lot of options for, those, what is the basis for that eigenspace? Yeah. Yeah. Yeah, so the multiplicity of the eigenvalue will be the dimension of the eigenspace, except for the defective case, which I'll just mention it, but I'm not going to go into it. Okay? Interesting. All right. What about this matrix? This is a shearing matrix. Shearing operation. Can you think about which vector, which direction stays the same? Which one? The x-axis stays the same. What about the rest? Are there other vectors that stay the same? Which one? The y-axis stays the same? No, I mean the green arrow was in the y-axis, and it stays in the same direction? No, it moves, right? Well, it's not the length. We said that AV equals lambda V. It has to be just the same direction, the result. The direction has to stay the same if it's an eigenvector. Yeah. It is a defective matrix, actually. It's a shearing matrix, and it has an eigenvalue 1 associated with the vector 1, 0, right? Because you see 1, 0 stays in the same direction, and it doesn't scale, right? So you can kind of immediately see, oh, there's eigenvalue 1 associated with 1, 0. Okay? Just without even calculating. But we can calculate. Okay? Here's the matrix, 1, 0, 1, 4th, 1. Here's the matrix. This is outside the class scope. I'm just going to show you quickly. Okay? You compute the determinant, 1 minus lambda, 0, quarter, 1 minus lambda. You get 1 minus lambda, 1 minus lambda, minus 0 equal 0. That's the determinant. So you got multiplicity of eigenvalue 1. Okay? Multiplicity of eigenvalue 1. Now we compute 1 minus 1, 0, quarter, 1 minus 1. We end up with the null space of A minus I is the null space of 0, 0, and 1/4, 0. That's kind of like the non-trivial non-space is actually just one-dimensional space as opposed to 2. So I said it's supposed to be 2, but not. But this is a, so basically, this is the vector, right? 1, 0. It spans it, but it's one-dimensional space. How can that be? Well, this matrix is, in fact, defective. That's one of the only cases. Not very common, but sometimes happens. I don't want to stick there. Okay, what about this matrix? What kind of matrix is that? Rotation, right? Like we talked about rotation matrices, right? Like it's part of your thing. Okay, which eigenvalues stay the which vectors stay the same? In the same direction? None. None stay the same. This is a 90-degree rotation. None of the vectors stay the same. Holy cow. None of the vectors stay the same. So how many, what's the eigenvectors and eigenvalues? They have to be complex. Okay, that's the case where you have complex eigenvalues. Rotation matrices have complex eigenvalues and complex eigenvectors. Then it works. But without having the complex value, it doesn't work. Except, I know what you're going to say. Except, what about 180-degree rotation? 180 rotation. Do you have any real eigenvalues and eigenvectors? Is there some vectors that stay the same? Yeah, it's the one that is reflected, right? Like everything is reflected about an axis, right? Okay, so then that is the case. That's the only case for rotation is when you have a 180-degree thing. Oh! This is all about memory. It's like, oh, remember when we talked about that? Remember we talked about transition matrices and how I suck compared to my colleagues, which are amazing. What can I do? Amazing thing about Berkeley is that they have amazing colleagues and amazing students. That's the best thing about being here, to be honest. And that's God's honest truth. It's truth. You know, in Australia, I traveled in Australia, and they have a shortcut for, they like shortcuts. They shortcut everything. So instead of God's honest truth, they'll say, Oh wow, truth. Truth. You know, that's God's honest truth, but it's just, okay, it's true. Okay, anyway, that's beside the side point. I want to revisit this in terms of eigenvalues, eigenvectors, and all kind of stuff. We talked about the steady state stuff, right? And we saw that the steady state was associated with eigenvalue 1, but this is a 4x4 matrix. It has more than one eigenvalue, right? It does. And if you remember, we had the situation where, hey, I had the steady state, and I said, oh, the steady state was 0.12, 0.24, 0.24, and 0.4, and when I do like this and like that, it stays the same, and hence, this actually satisfies A minus I times V times X equals 0, right? And or A times X equals 1 times X also, right? So that's eigenvalue, eigenvector with associated eigenvalue 1, right? This one? Okay. How did I get there, if you remember? That was a steady state. I got there by first computing many times. Like we started with x0 being 1/4, and then I computed A times this vector, and I got this, and then I computed A times this vector, and I got that, and then I computed A times this vector, and I got this, and eventually, after 100 times, I converge into the steady state. And then we said, oh, that steady state, it's not going to change. But like, why we converged? Why do we get there? How do we know that we're going to converge? Right? As you maybe took it for granted because like I'm an instructor and I've been here for a long time. But like you should not believe me. Why? Why did we converge? I mean, we just multiply A times the vector, and then took the result, multiply A again, and took the result, multiply A again, and took the result. I want to look now in terms of the eigenvalues and vectors of A to see why this is happening, and whether that's actually going to happen at all. Okay? In a transition matrix. Remember, when we looked at transition matrices, I showed you a few times. I showed you the Dead Sea, and as an example where things can shrink to 0. I showed you this explosion thing where things can actually go and explode. Then I showed you things that are conservative. But how did they look from an eigenvalues point of view? Now, is that useful? Think about it. Let's say you have some matrix representing an airplane, and then you have some initial condition to the airplane, and then that's a state, and you want to then multiply the vector to see what's going to happen. And then suddenly, the airplane starts, not being stable. How do I know that the airplane is going to stay in the same position, for example? Right? If I'm heading straight, like, pilots for 747 or 787, they like going straight mostly. Right? So they go straight, and then the matrix applied to them, and it keeps going straight, like it doesn't change. We don't like the situation where, this goes this in airplanes, right? So how do we know that this is not going to happen? Suddenly, the airplane is just going to change course. No problem. So we started before, when we talked about this transition matrix, we started by thinking about it from a context of, let's start with equal kind of allocation, right? Equal amount of people in each website. So we said we put 4, 4, 4, and we started some initial condition. Then we started propagating the system, and we got to a steady state. So I want to think about a general initialization for a transition matrix system. So we start with some initialization, and I want to know what's going to happen to it. Okay? We're going to assume a few things when we analyze this. One, we're going to assume that lambda i's, all the lambdas are distinct. There's no repetitive ones. Okay? All of them are distinct. That also means, and if it's not, then it still holds in many cases, but I just want to talk about it. It's just simple to explain this way. That also means that the span of all the eigenvectors spans Rn. So we can represent any vector by a linear combination of those eigenvectors, okay? That's the first assumption that we're going to make. Okay. So now I start with some arbitrary state, x0, and I take my matrix, multiply by that vector, and I get x1. That's my next step. My airplane, take velocity, direction, acceleration, amount of power, all that stuff, and then a times that, it keeps in the same direction. Good. Maybe. I don't know. Maybe that's something else. What is x1? Well, it's a times x0. Great. But I don't want to think about x0 as times x0. I want to see x0 in terms of the eigenvectors, because then I know things about that system, what the system is going to do to that x0. Because I know for some direction, things are going to stay the same. For some other direction, we're going to shrink. Some other direction, we're going to explode, right? Like, expand. So let's see what is x0 in terms of the other eigenvectors. So x0 is within Rn, so I can describe it as a linear combination of all those eigenvectors. Can I do that? Can I take the vector x0 and describe it by a linear combination of the rest? Yeah, that's exactly what I said. So there are some alpha 1, alpha 2, alpha all the way n, such that when I do a linear combination of those vectors, I would get x0. I don't know what those alphas are. I can solve for them for sure. Like if you gave me a specific x0, I can solve for them. Okay? How do I solve it? Gauge elimination. Okay. But I want to understand. Hold on. So alpha 1 times v1. Can I just take the a and put it in front of the alpha 1? And can I take the a and put it in front of the alpha 2? And so it's just like they're multiplying the vectors and expand the brackets. That's what I'm going to do. I'm going to expand the brackets. And I'm going to write alpha 1 times AV1, alpha 2 times AV2, alpha 3 plus AV3, alpha n plus AVN. Okay? Well, hold on. I've got now AV. What is AV1? V1 is the eigenvector. AV1 equals lambda 1 V1. What is AV2? Lambda 2 times V2. What is AV3? Lambda 3 times V3. Simple. In that case, everything is just going to scale depending on the eigenvalues, which I know. Because we're going to assume that we know them. Wow. So it's alpha 1, which is some component, and then lambda 1 times V1, plus alpha 2, lambda 2, V2, and also so on and so forth. Wow, that's pretty cool. So that's what I got. Some components shrank, some components expanded, some components stayed the same. Okay? That's what happened. But now, I want to compute x2. What is x2? X at time 2. What is x at time 2? X at times 1 is a times x at time 0. X at time 2 is a times x at times 1. Okay, let's see what happens. x2 equals a x times 1. But hold on, ax at times 1 equals to all of that. That are coefficients times the eigenvectors. Wait a second. So you got a and all of that. But look, the same trick that I did over here applies here. So A is multiplying, really, these are just coefficients, right? So it's A times V1. What is A times V1? Lambda 1 times V1. So basically, now my lambda 1 is going to be squared. And my lambda 2 is going to be squared. So I'm going to open it, and I'm going to get alpha 1, lambda 1 squared plus V1 times V1 plus alpha 2, lambda 2 squared plus V2. So every time I'm multiplying the matrix by the result of the previous time, I'm adding a power to the eigenvalues. So x2 equals to, all that with the power of 2. What about x at times t? You do that, and then you end up with alpha 1, lambda 1 to the power of t times v1. And so on and so forth. You know what this is? It's a mistake from the past, remember? Okay, well, at time t, you've got this one times, power of t, and this times power of t, and so on and so forth. I want to know at steady state. What is steady state? It goes to infinity, right? Like after many, many times. So now we can take it to the limit to infinity, where t goes to infinity, and see what happens. So limit of t goes to infinity of x of t, what will it be? Well, you just take these lambdas, and you take it to the power of infinity. Now the real question is, what are those values of lambda? What if lambda is very small? Let's say lambda is less than 1 in terms of magnitude, and I take it to the power of infinity. What if I take some number between 0 and 1, and I take it to the power of infinity? It'll go to 0. What if lambda equal 1, and I take it to the power of infinity? Doesn't change. And what if it's bigger than 1, and I take it to the power of infinity? Explodes. Whoa, that is useful, because if I know, if I have any magnitude of lambda I is less than 1, that component is going to decay to 0. Any other component, so if I have lambda 1, that stays the same. Anything that's bigger goes to infinity. And if I have some negative, then it's just going to kind of oscillate, like a positive, negative kind of stuff. Okay? That's pretty cool. So guess what? That matrix over here that we did the page rank on and found the steady state has lambda equal 1, that, right? That's what we solved for. That's the steady state vector, right? That's the lambda equal 1. But you know what? It has lambda 2 is 0.092, lambda 3 is 0.091, and lambda 4 is actually 0. What does it mean that the lambda 4 is 0? Is that matrix invertible? No, I can't even go back in time for that matrix. That was a transition matrix that is not invertible. Okay, that I found by looking at the eigenvalues. Okay, these are the eigenvectors. Okay, these are the eigenvectors. Now the question is, why, when I started with 0.25, 0.25, 0.25, 0.25, and I computed a times that, a times that, a times that, a times that, why did I converge to this value? Well, take a look at these. Right? I effectively took a power of something that's much smaller in magnitude than 1 many, many times. And so any component in the direction of this vector shrank to 0. Any component in this direction also shrank to 0, and this is also 0. So I was left out with that. So what I can do is I'm going to ask, x of t is a to the power of t times x of 0. Okay? So when I start with 0.25, 0.25, 0.25, and 0.25, what is that really? I can represent that as a linear combination of these vectors. Well, I need to find what are those coefficients. I'm not going to now solve it for you. I'm just going to give you the solution. The solution is 1, 0.34, 0.15, and 0. You need to take 1 of V1, 0.34 of V2, 0.15 of V3, and 0 of V4. Okay? That was the linear combination. Okay. So this is 1 times that, 0.34 times that, and then 0.15 times that. What happens when I take that many, many times? Effectively, I'm taking the power of those eigenvalues to the power of t. These eigenvalues are less than 1. Right? Actually, this is not exactly what happened. I'm taking the power of these to the power of t. So these would converge to 0. These would converge to 0. And the only thing that we're going to be left out is the component that was in the direction of V1. Does that make sense? So a to the power of t times x0 is 1 times V1 plus 0.34 times V2 plus 0.15 times that. And then if I express it in terms of the eigenvalue, then it's 1 times 1 to the power of t. That's the eigenvalue to the power of t. 0.34 times, here's the eigenvalue to the power of t, plus 0.15, here's the eigenvalue to the power of t, and then this is. And when I take it to the power of t, this will die, this will die, and this is dead already, and I end up with V1. That's why we converged. That's what we converged. Now, my question is, what if the eigenvalue associated with V2 was lambda for that one was 1.001? What would have happened? This would explode. This would explode. Okay? This would go to hell. And we would not converge into a steady state. What if the eigenvalue associated with lambda 2 would have been 0.99? Would we converge? Yes, but probably we need like 10,000 times or something instead of 100. You know, how fast it goes to 0, that makes sense. So now, think about an airplane. Let's say an airplane, a system, has some eigenvalues that are 1. Let's say it has some eigenvalues that are small. And let's say it has some eigenvalues that are bigger than 1. And let's start with an initial condition. Okay, and see what happens. If my initial condition is in the direction of the eigenvalue 1 or the smaller values, I'm going to kind of like, okay, well, yeah, then it will decay. Okay? It will keep only those in the direction of eigenvalue 1, but all the components in the direction that are smaller than 1 kind of decay. So let's say I shift it, I shift my airplane. The airplane now goes a little bit high, and then it goes back to the original direction towards eigenvector 1. What if I have one of the eigenvalues bigger than 1? I shift my direction, so a different initial condition, and now I let it evolve by itself. Okay, I'm not going to control it anymore and see what happens. Well, I picked a really bad case, and suddenly, my airplane goes out of control. Unless I do something, right? Unless I explicitly put it back. But if I let the airplane do whatever it wants, if it has eigenvalues bigger than 1, it will just explode. That's why it's important to understand eigenvalues of a system. Does that make sense? Okay. So just to be clear that I'm kind of... so actually, yeah, I don't want to talk about it. So any questions before we finish today? Yeah. If the eigenvalue is -1, then you kind of alternate between two states. But it doesn't explode. It doesn't explode. Folks, have a nice weekend. And Monday, there's discussion. Last homework before the midterm is on Friday. Study well for the midterm. And then after that, next week, circuit starts. Second module. Thank you so much. Maybe. You too.
So I was just wondering, you said that the calculating the eigenvalues is more computationally efficient than just doing the matrix multiplication.
That's not exactly what I said. I said that if you know the eigenvalues and eigenvectors,